Greetings! Welcome to Electronics2. This is lecture number 7 and I am Razavi. Today we will talk about a new circuit topology that we have not seen before, namely the differential pair. And to get there we will have to go through some motivation, some background. So we'll talk about the problem of noise coupling as a serious issue in many electronic systems. And then we'll talk about differential signals, what we exactly mean by that and how they differ from the signals that we have seen in the past. And finally we will arrive at the differential pair and begin to analyze it. We want to get comfortable with it, we want to analyze it from different perspectives and then see what benefits arise from the circuit compared to the circuits that we've seen in Electronics 1. Okay, so, but before we go there, let's review what we had in the previous lecture. In lecture number 6, we talked about current meters. And we saw that the idea is to inject a constant, well-defined, stable current into a diode-connected device to generate a magical VGS, which is then applied to these other MOSFETs. And if we pick all of these lengths of these transistors to be the same, then the currents are simply scaled according to the ratio of the W's, the widths of these transistors. So I2 will be just W2 over W1 times Iref, and so on. Okay, and then I pose this question to you before we concluded that last lecture. We have a source follower receiving an input signal here and generating an output signal here, and it is biased by means of a current source. This is an NMOS current source. And for our reference, we also have a reference current that goes to ground. This ground is hardwired. So the question is, how do I bring the information from here to here? What we did in the past was cheating a little bit. Here, this was a P-type current source because it was coming from VDD to a node in the ground, and I copied it to N-type current sources. But here, I don't have that flexibility. The current reference is to ground, it's not from VDD. So how do I go from here to here? Okay, so the answer is pretty simple. What we will do is we will connect this to a diode-connected PMOS device. That's really the only option we have. There's nothing else we can do, right? And that gives us a magical VGS. We can copy this current onto another PMOS device. So we connect this to a PMOS device here. This is, of course, all VDD. So far so good, right? This current is a good copy of this current. Now I need to somehow take this information to M2. So now I pretend that this current is a reference current, like this guy, right? This is a p-type current source, just like this. So I have to inject it into a diode-connected NMOS device to create the magical VGS that I need, and then give it to M2. So we will connect this to a diode-connected NMOS device, and then we give it to M2. So you can see what's happening here. This current is copied over here into a PMOS device. Then this PMOS injects it into a diode-connected device and is copied now to an NMOS device. How we choose these dimensions is somewhat arbitrary. We could play with different values. So for example, if this current is supposed to be twice this current, I can make this one equal to this one, and then this one just twice this one, right? There are different combinations. And also, as you can see, here I made a copy of the reference, and then I made a copy of the copy. So as we keep cloning a clone and another clone from this clone, eventually the quality of that current source degrades, meaning that this current source is not as good, as stable as this current source, because this is a copy of this. For example, if there are some asymmetries between these two transistors when you build them, if there are some mismatches as we call them, then this current source will not be as good as this, just the way this is not as accurate as this. It's almost as accurate. So that's something that we have to consider in more advanced courses. Okay, all right. Now, before going to today's discussion, I also wanted to go back to what I showed you in the first lecture in this series and see if what we have learned so far has any role, any significance in the context of some of the circuits that we just looked at before. So remember the 741 op amp that I showed you before? Okay, so again, you don't have to draw this. I just want to show you a few things. All right, well, we had no idea what was going on here. But now, if we look more carefully, we might recognize some circuit topologies. In particular, let's look at these two. Let me change the color of my pen. So we'll go to full view, and then we change the color to maybe red. So let's look at this configuration. We recognize this. This is a current meter realized by PNP bipolar transistors. So this is a current source that you would like to create, and the reference current is coming this way, right, through this branch. Now again, we won't go through this and see what's going on, but that's, at least that's something we can recognize. Okay, there are some other current meters here, like these two, but they are more complicated, so we won't discuss them here, but they are really fundamentally current meters. We can also see another current meter here, right? So again, we have a diode connected device in PNP, another one here, so they have the same base emitter voltage, so we copy this current over here. Okay, so this is another one. It's a little more complicated because this has some resistive degeneration, but overall we can recognize some of these things. Okay, how about the MOS op amp that we saw before? So again, you don't have to draw anything, just see if we can recognize any of these circuits. Well, do we recognize these two as a current meter? This line is not connected, so we have a diode connected device here, and this VGS is applied to this one. So these two form a current meter. Similarly, these two form a current meter. Again, don't worry about this line. See a diode connected PMOS driving another PMOS device. So that's another current meter. Do we recognize anything else? We can actually see a cascode structure here. Look at this PMOS and this PMOS. the source of this PMOS is connected to VDD, the gate to some bias, the drain is connected to the source of another PMOS device. The gate of that PMOS device is connected to some bias, and the drain is available. So this is a cascade current source. You can see that this is a cascade current source. So now some of these things actually begin to look interesting and familiar. All right, you can also see a cascade NMOS structure here if you look very carefully. Right, you see that we have an NMOS with the source grounded, gate going to some bias, actually coming from a current meter. And then this is another NMOS device with its source connected to this drain. So these two form an NMOS cascade structure. Okay, so far so good. We begin to see certain things. Now there's another structure here that is curious and intriguing, but we have not studied. Look at these two transistors. You see, their sources are attached to each other, and there is a current source down here. And they have two gates connected to V in plus and V in minus. Okay? So that's an interesting circuit, right? It's symmetric. Two NMOS devices, they have the same dimensions. You can even see the dimensions of the transistors. And there's a current source on the bottom. So what is this? We will have to see. This is actually what we call a differential pair. So we don't know what it does and why it's here, but at least we can see something. Okay, so continuing on, we can see from this paper also the circuits I showed you again in the first lecture. And again, the question is, what's all this stuff that we see here, right? So again, we see this symmetric circuit topology, right? You have two transistors with a current source, two transistors with the sources attached to each other, and a current source going down to ground. Similarly here, similarly here, similarly here. So that becomes an interesting circuit that we should look at, right? What is this? What does it do? You see, it's another one, you see? It's all over the place. So what's all this for, right? So this circuit is another beautiful invention in electronics that has been around for decades, and even today is used extensively because it has many nice properties. Okay. All right, so with these introductory remarks, we can now go ahead and talk about the problem of noise coupling. So let's talk about that. All right, so we don't exactly know what noise is. Don't worry about it. It's something that we don't want, right? So I'll give you an example to see what we mean by noise. All right, so you're familiar with the electrocardiogram system. This is what we call ECG. This system measures our heart activity, right? So the electronics of the system is actually quite interesting, and we would like to just get a glimpse of that. So how do we measure the heart activity, the heart rate, etc.? All right, well, here's the human body. And what we do is every time there's a heartbeat, our body generates actually an electrical signal on the surface, on the skin. So we can measure the electrical signal. And that electrical signal looks like this as a function of time. Okay? So this is the signal that our body generates every time there's a heartbeat. So you get one, then maybe a second later you get another one, and so on. This voltage that we measure is not much. It's on the order of millivolts. Okay, so we'll just say approximately millivolts. Okay, so let me clean this up. So it's on the order of millivolts. a few millivolts. Okay, so it's a pretty small signal. All right. Now, an ECG system operates as follows. We attach an electrode to the arm of the patient right here. So we attach an electrode here and bring out a wire. That becomes the signal. Then we attach a wire to the ankle of the patient also and bring out that. This becomes ground. Now we give this to some sort of amplifier. So here's an amplifier. The amplifier has its own ground, so these are connected to ground. And then we amplify, right? So amplifier. We amplify the signal and we get something. So for example, I amplify it by a factor of 10. So I go from a few millivolts to maybe 20, 30 millivolts. Okay, and I can do more. So in practice, we actually take this to what we call an analog to a digital converter, right? What we call an A to D, ADC, analog to digital converter, so that we convert this analog information, this analog waveform, to a digital representation, and they can perform processing on the signal in the digital domain. What's interesting is that a doctor, a cardiologist, looking at this waveform can tell what's wrong with your heart. From the shape of this part of the waveform and that part of the waveform, etc., he can tell what's going on. So that's interesting. Okay, so now when we construct a system like this, we have one major problem. So let me change the color of my pen to show you what the problem is. Well, we are trying to sense a signal on the order of 1 or 2 millivolts. But in addition to that, we have something else coming in. Remember that we are in a room, and there are these electrical wires all over the place, right? In the walls, overhead, etc. These electrical wires are carrying the line voltage, 110 volts, 60 hertz in the US, 220 volts, 50 hertz in other countries. And all of these lines couple that 50 or 60 hertz noise into this line. So this line is picking up a lot of the voltage that's going around, the AC mains voltage. So this would be, in the US, it would be 60 hertz. In other countries, it will be 50 hertz. So we are picking up that noise. So then what comes out of this amplifier is actually quite dirty, because we have, as a function of time, this small millivolt heart signal plus perhaps a much larger 60 hertz or 50 hertz line voltage. So that looks like this. The line voltage looks like this. It's coming at 50 hertz or 60 hertz. And then on top of that, we have these things, right? So we have one for one heartbeat, another heartbeat, and so on. So you can see that the desired signal is heavily corrupted by this noise that is coupled to this line from the environment. Okay, so this is a serious problem. All right, so what we do in practice is the following. We will attach one more line to the patient. So let me change that to green. So to the other arm of the patient, we attach another electrode. Okay, so one on this arm, one on this arm. And we give both of these to an amplifier that has two inputs. So if you call this V1 and we call this V2, this amplifier is like an op amp, right? Not quite an op amp, but like an op amp. It subtracts these two, so here it will generate V1 minus V2. Now if these two lines are nicely packaged together so that the two pick up the same amount of noise from the 50 hertz or 60 hertz, then yes, this will have some noise on it. We'll call it Vn for noise. But this will have the same amount of noise, so this will be also plus noise. So V1 minus V2 will have no noise. So has no 50 hertz or 60 hertz noise. Okay, so what we did here is we went from one line carrying the desired signal to two lines carrying the desired signal. Of course, our hope is that V1 minus V2 is not zero, meaning that V1 and V2 don't look the same. And they don't, because one is attached to this arm, one is attached to this arm. Okay? All right. So these two lines together carry the desired signal now. And that forms the basis of what we call differential signals. So I have to formally introduce differential signals, but we can see from here what will happen. Okay, so let's go and talk about differential signals. All right, so by a differential signal, we mean one that has that differential signals are two signals. As you can see here, there are two. And we have a very strict definition for them. So as a function of time, this is what they look like. So let me first write it in words. Differential signals have to have two properties. A, they vary by equal and opposite amounts. What does that mean? It means that if one of them is going up, the other one has to go down, and they have to change by the same amount. So let's start from here. For example, V1 and V2, right? So V1 wants to do this. Okay. V2 has to do this. So V1 goes up and comes down. V2 goes down and comes up. And by the same amount. So if this goes up by a peak value of 2 millivolts, this goes down by a peak value of 2 millivolts. Okay. The second condition that is also necessary here is that they have the same average, or as we call it, DC value. So if I continue this waveform for a while, what I should see is this. That I should see this goes up and down, let's say as a sinusoid. This also goes up and down like that, and they have the same average value, which is this one here. Okay, so this average value actually has a name. We will call it VCM, and we will call this the common mode level. Okay, so now some new concepts. We just have to take them slowly and digest them as we go along. All right, so here's where we are. We are defining differential signals. So we have two signals, V1 and V2. Let's say just sinusoidal signals for now. We need two conditions for them to be differential. Number one, when one goes up, the other one goes down. So here this one goes up, this one goes down by the same amount. Number two, they have to have the same DC level, the same average value. So as this goes up and down around this DC level, this also goes up and down around the same DC level. So just as a quick note, let's try to plot V1 and V2 if they do not have the same average value, meaning that they don't have the same common mode level. Okay, so here. So not differential. Okay, so I will draw two signals that are not differential, even though they satisfy condition A. So here it goes. You have one that goes up and down like this, another one that goes up and down like this. And one has this much DC, the other one has this much DC. So you see that they do vary in opposite directions. They're like 180 degrees out of phase, but they have different DC levels. This one is shifted down with respect to this one. So this is not considered a differential signal. Okay, so this term is important. We will use this extensively. So the DC level of both of these, which is the same, is called the common mode level, meaning that it's a level that is common to both signals. They have the same level, the same DC level. All right, so that is the definition of differential signals. Okay, let me see where we are and what we need to do. Okay, so let's try to write some equations for these signals, see what they look like. So V1 of t, what should I write for it? It's a sinusoid, for example, right? Okay, so I'm going to say that the peak value of this sinusoid is V0, from here to this peak, right? Also from here to this peak. So if that's the case, I can say this is V0 sine of omega t. Now this function has a 0 DC, 0 average level. But I know that the average level of each of these waveforms is not 0. This is not here, right? There's a shift of VCM. So this has to be plus VCM. So that's the equation for V1 as a function of time. Okay, how about V2 of t? Well, V2 is similar. It has the same DC level, right, VCM, except that it goes in the opposite direction. So this would be minus sine, right? So V2 of t will be minus V0 sine of omega t plus VCM. Okay, so these are the equations that we have for V1 and V2. Okay, that's pretty easy. Let's just look at this example. Determine the peak and peak to peak amplitudes of V1 of t, V2 of t, and V1 minus V2. Okay, so here's what I'm interested in. V1 of t is a voltage by itself with respect to 0, with respect to ground, right? So if you measure V1 with respect to this ground, there's some voltage, let's say a sinusoid, and it goes like this. It goes up and down like this. It has this much DC. It has a peak value of V0, and 0 is here. V2, similar. V1 minus V2 is a different function, right? V1 minus V2 is the difference between those two equations. So for each of these, we want to find the peak amplitude and the peak to peak amplitude. Okay, I'm going somewhere with this, so you need to be patient. Okay, all right, so we'll construct a little table. So we say peak amplitude and peak to peak amplitude. Okay, these are the numbers we're interested in. And then what we have are V1, V2, and V1 minus V2. What is the peak amplitude of V1? Well, as we saw in this waveform, it's just V0, right? From here to the peak is V0 from the DC value. You can also see it here. So that's V0. And similarly V2, V0. How about V1 minus V2? What's the peak value of that? Okay, so V1 minus V2 will be 2 V0 sine of omega t. So let's write that here. V1 minus V2 as a function of time is 2 sine of omega t. 2 V0. Let's erase this. Okay, it doesn't erase. That's interesting, isn't it? Okay, so we'll just cross this out. 2 V0 sine of omega t. So the peak amplitude of V1 minus V2 is 2 V0. So that's 2 V0. And that makes sense, right? Because you're subtracting the negative number from that number, so everything is doubled in amplitude. All right, how about the peak-to-peak amplitude? The peak-to-peak amplitude of V1 is from here to here. So that's 2 V0. That's 2 V0. Similarly, here is 2 V0. And then here, well, from the positive peak to the negative peak, we have 4 V0. So that's 4 V0. This seems trivial, but in reality, you and many of your colleagues and many people out there keep confusing these things. Okay? There are all these different things. Peak amplitude of V1 or V2, peak-to-peak amplitude of V1 or V2, and then peak-to-peak amplitude of V1 minus V2. So these can be really confusing, and it's important to keep all of them clear in your head. Anytime in doubt, you can write the equation or draw the waveforms and make sure that the answer is correct. Okay, very good. Moving on. All right, so the next question that would be good to answer is the following. How do we generate differential signals? Okay, so here's a common situation. I have a microphone, this microphone here, and it generates just a single line, like this V1 here, okay? It doesn't generate the other one. So here's a microphone. The microphone has a ground, and it generates a single signal here. Okay, so it's some waveform, let's say just a sinusoid. But I would like to take this to somewhere that needs differential signals. So it says, no, I want both of these phases, both of these waveforms. So I need to generate out here something like this, and then inverse of that, something like this. So how do I go from here to here? What box do I use to perform that function? Now there are many possibilities. I will show you one example. One example is a transformer, which you've seen from basic circuit theory. The transformer has a primary and a secondary. So you have a primary and a secondary. The primary connects to the microphone and the ground. The secondary connects to these 2 points. And what it does is it generates these two, which will be differential signals. Now, we don't necessarily use a transformer all the time. Sometimes we use other types of circuits and devices. But this is just one example of how we can go from this signal to these two. Okay, I would like to introduce one more term here. What we saw before was the concept of the common mode level, which is just a DC level of both of these waveforms. Now we're going to introduce one more term, and for that I will change the color of my pen again to maybe this one. Okay, so you see the signal here. We call this a single signal. Well, we have actually a more precise term for it. We call this a single-ended signal. So a single-ended signal is one that is measured with respect to ground. Okay, it's just one signal, like all the signals we've seen in electronics, one, right? Is measured with respect to ground. That's what we call a single-ended signal. This is in contrast to these two, which form a differential signal. A differential signal consists of two of these. So this is single-ended and this is single-ended, right? This was a single-ended waveform. This was a single-ended waveform. But together, they formed a differential signal. So a differential signal actually consists of two single-ended signals. Here's one with respect to ground. Here's another one with respect to ground, and they just happen to go up and down in opposite phase, meaning differentially. Okay, so we're done with differential signals, and now we can go ahead and I just wanted to give you a quiz before we go to differential pairs. So let me write the quiz here because I don't want to leave this page. Let's suppose that this microphone generates a signal and travels on this line and it gets to this transformer, okay? And let's suppose that, remember we talked about the 60 hertz or 50 hertz noise coming from the lines, from the environment? Okay, so what we would like to study is the following. If there is noise coupled to this line, what happens? And a different case, if the noise couples equally to these two lines, what happens? Case number one, case number two. Okay? I'll give you 1 minute to think about it. Okay, so case number one. The 50 hertz or 60 hertz noise from the lines around us couples to this line. What happens? Is the signal corrupted or not? Yes, the signal is corrupted before it is converted to differential. So then we can't do anything about it, right? Even if we convert to differential, because we already corrupted the signal by this noise, converting it to differential does not help. The difference between these two still has that noise in it. Case number two, the noise from the lines couples to these two lines, okay, the 50 hertz or 60 hertz noise. Not here, but here. If it couples equally to these two lines, we are back to this scenario. We are coupling to both of them equally. So the difference between these two is free from that noise. That noise is gone in the difference between them, just the way this had no noise. Okay, so we have to make a distinction between where exactly the noise might be injected, might be coupled, right? Some places are sensitive to noise, some places are not sensitive to noise. All right, let's continue and introduce the differential pair now. Okay, so we saw differential signals. So now we can talk about the differential pair. So the differential pair. Okay, the differential pair looks like this. It's a symmetric circuit. We draw it in both bipolar and CMOS technology. It has a current source going to ground. It has two inputs. Okay, that's the difference with respect to the basic amplifiers that we saw in Electronics 1 or the cascade amplifier that we saw here. So we might call this V in 1, this one V in 2. There are two resistors here going to the power supply. So this is VCC and another resistor here. We call this RC here, RC here. And there are two output nodes. One here, we call it X for now, and one here, so we call this Y. Okay? All right. So this seems rather complicated compared to the structures that we have seen before. But not a problem. We will analyze it extensively and we will understand it very well. All right. So the circuit is nominally symmetric, meaning that if I draw a line here, this transistor is identical to this resistor is identical to this. And this current source goes to both of them. So you see here is another place where we need to use a current source. So everything that we learned about current sources and cascodes and current meters becomes handy here as well. All right, so for the MOS version, we do the same thing. So here's, maybe I'll draw it down here. So again, two resistors, two MOSFETs, like this. We have a supply voltage, we call it VDD. Two resistors, we call them RD. Two inputs, V in 1, V in 2. A current source down here going to ground, and we have an output here and an output here. So these circuits are different from what we've seen before. They have two inputs and two outputs. The closest thing we know to these circuits is the op amp, right? The op amp as a black box to us had two inputs, positive and negative, or inverting and non-inverting, right? And then one output. But here actually we have two outputs. So we'll see what that means and so forth. In fact, at the input of an op amp, you might see a circuit like this or a circuit like this inside the op amp. Okay, so the circuits have a current source on the bottom. We have a name for this, IEE, and this one is called ISS, just a name, anything you want. We have two inputs, V in 1 and V in 2. These two inputs will be differential signals. So if V in 1 is going up at a given point in time, V in 2 is going down. But they have the same DC level, the same common mode level, and the same here. All right. So we need to study these carefully. We need to understand what exactly happens. Why is it interesting that if I have V in 1 and V in 2 and these are coming as signals, differential signals, what does the circuit do exactly? How is this current flowing from this transistor or that transistor? And what do the voltages at X and Y look like? Right? There are all these interesting questions that we have to address, and that's okay, all in good time. All right, so that is the basic structure. Right now we have no idea what it does, but that's okay. Again, we'll study it carefully. Let me see. Okay, I will need to do a quick review of the common emitter stage before we go in here. So, review of common emitter stage. So here's what we had. Remember, a single transistor Q1, RC, VCC. Let's suppose that there's just a battery connected between the base and the emitter. So we'll call this VB. And let's assume that this device operates in the forward active region, as these do. And then I would like to find this voltage here. How much is this voltage? So let's call this V out. Can I find that? It's a bias calculation because we don't have any signals, right? We have a battery between here and ground, so let me draw that battery explicitly so that you can see it. This is a battery called VCC, right? And I would like to find this voltage, just the DC voltage, the bias voltage. Okay, well, this transistor is an active region, and it has a base emitter voltage equal to VB. So we can calculate its collector current, right? IC is equal to IS of the transistor exp of VB over VT. This current flows through the resistor and generates a voltage, according to Ohm's law, equal to ICRC. So what can I say about this voltage? Well, let's write a big KVL. We have a loop. VCC is equal to this voltage plus this voltage, right? So I can say VCC equals to ICRC plus V out. So V out is equal to VCC minus RCIC. That's what I would like you to remember, because we will need this in the analysis of the differential pairs as well. Okay, so what this means is that the output voltage between the collector and the emitter is given by this supply voltage minus this ICRC. Okay, that's what we need. So next time we will delve into this differential pair and study it first intuitively and then analytically, and step by step build up our knowledge. I will see you next time.